Hello everybody, Mr. Hasty here. Today we're going to continue section 7.5 and discuss the work done moving fluids. So real quick refresher, work is force applied over a distance with the formula, the general static formula, work equals force times distance, or in calculus often, work is going to be the integral of a force function integrated over a distance. Now, the units for work are a Newton times meter, Newton meter, also called a joule, or a foot times a pound, commonly just referred to as a foot-pound. Can be written either of those ways. So when you work with fluids, one of the things we talk about is the weight density of the fluid. What a weight density is it's a measure of force per volume. And for our examples, we are going to be working with feet per cubic pound. So as an example, water is 62.4 pounds per cubic foot. I said it backwards earlier. So 62.4 pounds per cubic foot. So that means that if we have 1 cubic foot, that means literally 1 foot by 1 foot by 1 foot cube. That would weigh 62.4 pounds. And if we had 10 of those, it would be 624 pounds. Okay? Now, the reason why this is going to come up is because when we're talking about the amount of force to move a liquid, we're usually talking about moving that liquid. If we have a container, we're talking about moving that liquid upward. Now, in this case, the force we're talking about is the weight of the object. So we're going to have these measurements of liquids in pounds per cubic feet. If we want to know the actual pounds, we're going to have to multiply that by a volume. And so that's going to be kind of the logic we use going forward into our examples. So let's move on to our first example here. Given a cylindrical tank with a radius of 12 feet and a height of 10 feet filled to within a foot of the top with mercury, which is very heavy for its volume, having a weight density of 849 pounds per cubic foot, how much work would it take to pump the fluid to a height of 2 feet above the rim of the tank? So what's important to note, we have the dimensions here. The radius is 12. The height is 10. These are in feet. Now, a couple key notes. This is not filled all the way up with our liquid. Our liquid only goes to, let's see, it says within, where did it say it? Within a foot of the top. So our liquid's actually only 9 feet high, and there's going to be a distinction there between the height of the liquid and the height of the tank. But we need to move that liquid to a height 2 feet above the tank. So that would be at 12 feet up. So there's a lot going on here. So what we're going to talk about is how when you move something, the height that you move it to is what matters for determining work. So not all of this liquid's at the same height. Some of the liquid is at a height of 9 feet and thus would only need to move an additional 3 feet. I'll mark that. This is 3. An additional 3 feet, whereas the liquid at the very bottom would have to be moved all 12 feet. So what we're going to think about is we're going to think about slicing this into little discs of liquid. Imagine that we froze it and then we moved frozen slices. And we're going to look at each of those thin little discs. So if we have a thin little disc, now imagine it's really, really, really thin. In calculus, we do this thing where we talk about doing infinitely thin discs. So we're going to call the thickness of that disc delta x. So what do we know? We know the weight density of our liquid is 849 pounds per cubic foot. So what we would like to do is be able to find the weight density of one of these disks, or sorry, the weight force of one of these disks. So to get weight density and turn that into force, force can be thought of as weight density times volume. We're taking pounds per cubic foot and we're multiplying it by cubic feet, and that'll give us an answer in pounds. So how are we going to model that here? Well, the weight density we know is a fixed number. The liquid, mercury, always has the same weight density. The volume, if we're talking about one of these cylinders, is just the volume of a cylinder. And that formula is pi r squared h. Now, the nice thing about a cylinder is every one of these disks is going to have the same radius. So, our volume is pi times the radius. The radius in this case is 12 squared times h. This is the tricky part. The height of the disk is delta x. Now, we could call it delta x, we could call it delta y, depending on which dimension you want to do. I think the book calls it delta y. So now we have a formula for the force. This is our F of x. Now remember, we also have to multiply this by the height. How far is it going? Well, if we look at it like the bottom is where x equals 0, then we would have to move it 12. If the next disk is maybe at like x equals 1, we would have to move it 11. So to get force times distance, remember work, capital W, equals force times distance. In this case, we're going to call that our force function, 849 times, and I'm squaring the 12 here, 144 pi delta x. And we're going to call the distance it has to move. Now there's actually two ways to set this up. I'm going to call the distance it has to move 12 minus x. If it starts at 0 at the very bottom, it has to move 12. If it's up at the 9-foot mark, it only has to move 3, which is 12 minus 9. And there we go. Now because this has a delta x in it, that intuitively means it's going to be an integral. So for us to actually calculate a numerical work, we're going to do the integral. 49 times 144 pi. And I'm going to end up putting that delta x at the end just because delta x is dx. Now the next question is, what's our bounds? Well, remember, the first one down here is going to be at a height of 0. So we're going to start at 0. And this is where people make a mistake. Where do they stop? What's their upper bound? Some people will do 10 because that's the height of the tank. But the liquid that we're actually moving only goes up to 9. So those two represent the height of the liquid. Now, on a side note, there is another way to set up this problem before we get to the mechanical answer. It could be the integral of 849 times 144 pi. And instead of saying 12 minus x, you just call it x. So what that's saying is that this x represents the distance it's going to travel. Well, you start from the lowest distance you're going to travel, which is 3, to the highest distance you're going to travel, which is 12. And if you do these integrals, you'll be surprised. They actually come out to be the exact same value. So we're going to use our calculator here and do that work. We're going to get a rather large number, 25,925,302. And what would our unit be there? Well, work is measured in units of force times distance. So in this case, it'd be foot-pounds. A little low on space here. So let's talk about a general approach before we move on. So when we're doing a problem of doing work to move a liquid, what we're going to end up wanting to do is we're looking for force. And we're looking for work, which equals force times distance. So the way we're going to find the force, because we're always going to know the weight density of our fluid, right? And weight density is measured in units of pounds per cubic feet. To turn that into a force, we need to multiply by the volume of our disk. And so we're going to take our weight density times the volume of our disk. And that is always going to contain a delta, like a delta y or a delta x. And the reason for that is our disks, for us to apply calculus, our disks have to be infinitely thin, and that's what our delta y or delta x signifies. And then we're always going to multiply that by something that is the height. So we're going to need to establish two kinds of equations. Our weight density is going to be a constant. We're going to need an equation for volume. Sometimes that'll be a constant. In the last example, that was a constant. We're always going to need an expression for height. We talked about how there's two ways to view that, and there's actually two different ways to set that up. So we're going to move on to a second example, which is going to be a little bit trickier. All right. So example 2, a conical tank is filled to within 3 feet of the top of the tank. So we're going to have a gap of 3 feet. So I'm just going to label that 3 right there, and that's from here to here. With gasoline weighing 42 pounds per cubic foot, that's our weight density, 42 pounds per cubic foot. If the cone has a diameter of 10 feet, so this distance is 10 feet, and a height of 10 feet, so this whole distance is 10 feet, how much work would it take to pump liquid to a height of the rim of the tank? So we just need to go to the rim of the tank. So imagine that we have, and let's remember our general approach here. Work is going to be equal to the weight density times the volume times the height. Now we already know our weight density of 42, so let's talk about the volume. So the tricky part about this is, if we imagine our little discs, remember, they're infinitely thin, so we call their thickness delta. I'm going to use y in this case. You could use y or x. But the radius is not, for every disc, is going to be different. Because this is a cone, we're going to get smaller and smaller radiuses as we get deeper and deeper. So how do we come up with a formula for that radius? Because we are not going to be able to just use it as a one number, as a constant. So we can use some proportional reasoning, and we did this a long time ago. Basically, if we're worried about the height y, right? So our height y, which we'll call this measurement right here, compared to our radius r, is similar to the big cone. The little liquid cone inside is always similar to the big cone, so that means the ratio holds. So the ratio of the big cone's height to radius is height of 10 and radius of 5, which we could reduce. But that means we can call our radius, if we solve for radius here, we will get 1/2 y. Just cross multiply and divide as you see fit. So our formula for the volume of this is pi radius squared 1/2 y squared delta y. And then our height, well, if this is y and I have to get it to a height of 10, then my height in this case has to be 10 minus y. So because this has a delta y in it, it turns into an integral. I'm going to simplify here a little bit. The 1/2 squares and becomes 1/4, so that's how I got my pi over 4 right here. And remember that I'm moving the delta y to be the dy at the end. So let's discuss briefly what our bounds are. So if this represents y, our up and down height here, then the lowest you could ever get would be what we would call 0. But the highest the liquid's ever going to get is 7, because remember, the liquid is only within 3 feet of the top. Top would be 10 feet, so we're going from 0 to 7. And where this will make sense is because the lowest possible water at the very, very bottom is going to have a height of 10, whereas the highest water right here is going to have a distance to travel of 3. So we do this integral, and we get 17,914.539, and because we're working in feet and pounds, it'd be foot-pounds. All right, so next time we're going to be talking about fluid pressure, and so see you then.